So we're very happy to have Dipendra Misra here with us tonight. Dipendra is a PhD student at Cornell in Yoav Artie's lab. He is finishing up his PhD. He's done some interesting work. So his research is at the intersection of natural language processing, but he's also done a lot of work in fundamental RL theory and work at the intersection in areas like question answering, instruction following by embodied agents in virtual environments. So we're really interested in hearing a lot of the things that he has to say. So.
Hi. Thanks everyone for coming to my talk. I'm Dipendra Misra. I'm a PhD candidate at Cornell University. And I work at the intersection of natural language and machine learning, but the things that I'm kind of really interested in is designing natural language agents which can do interesting things for us. And today I'll be talking about situated natural language understanding. So the goal here is to do natural language understanding in context. And these are some problems where this setting arises. So on the left, we see these popular voice assistant applications. Is it turned on?
It's just for the camera. That's what
Oh, I see. Oh, OK. So you see these voice assistant applications on the left, like the Google Voice Assistant, Siri, Cortana, Alexa. And in the center, you see these robots which have to follow natural language instruction, and in this case, make some dessert. And on the right, we see these booking assistant, like dialogue-style agents, which have to interact with a human and book their flight. And these are very different applications, but they all have a natural language interface. And the beauty of natural language is that it allows non-expert users to provide a broad range of objectives to AI agents. So that makes it like a very natural fit for these applications. So let's look at these applications in more detail. So for the voice assistant applications on the left, by context, I would refer to something like the settings of the phone, and if they set an alarm, for example. And an action could be to cancel an alarm or to play music or to tell me the temperature. For the robots which are following instructions, the context is the physical space in which they are situated. And the actions would be the values that you give to the controller. And for these booking assistant applications, the context could be the prior history of conversation. And an action could be to generate a response asking for clarification or to print the itinerary or to book the flight. Now, these are, as I said, they are very different type of challenges. But as you can see, they have a very similar interface and a very similar set of challenges, too, which involves understanding the semantics, reasoning about the context, and then taking appropriate actions. So I will be mostly discussing my work on this problem in the center, which is called the instruction following or robot instruction following or agent instruction following. And we'll just look at these challenges in more detail. But before that, I'll give a brief background of my research, just to more appropriately situate where I'm coming from. So a lot of my research, as you've mentioned, has been on instruction following. And this includes some very early work on rail robots and some more recent work that have been using these more end-to-end deep learning style methods for this problem. And we'll be looking at some of this work today. The other problem which I'm very interested in is like question answering, or also like a more general problem is called semantic parsing, where you take a natural language text and you map it to a formal representation, which you can then use for question answering or something else. And some of my work has been on like designing systems which do semantic parsing for question answering. Now, both the problem of question answering and instruction following have a very similar nature, where you perform a sequence of actions and you get some kind of feedback, which is often delayed. And a learning framework which accurately captures this problem is reinforcement learning. And people have been doing it a lot for various tasks like playing games, but also more realistic tasks like question answering. And some of my work has been to understand what do these algorithms really do, and like can we prove guarantees, and under what condition can we say that that we can solve this problem accurately. So I won't be discussing this work, but if you're interested, I'll be delighted to talk to you about this after my talk. And finally, I really enjoy doing open source research, like creating production softwares, releasing them. It's a great way to give back to community, and it also helps you with like have fast reproducibility. So we have been like working on some softwares in our lab, including like some house simulations and learning framework, and we'll briefly look at it today in the context of the problem I mentioned. So that problem is instruction following. So in this case, there is an agent or a robot. You can use your favorite metaphor. It's situated in a physical or a simulated environment. and can observe the world in the form of, say, RGB images or some LiDAR or some other form of data. And it's given an instruction and has to map these instructions to actions in the real world. And it has to do so while reasoning about what it can do in the real world, but also following the instruction. And this like cartoon kind of accurately shows what the problem is about. The previous work, or at least until the last few years, have been mostly focused on approaching the problem by building these elaborate pipelines. So these pipelines have these models which are tailored to specific challenges in the problem. So as I mentioned, we have to reason about the context, the instruction, generate actions. So people have, like, for example, built pipelines which have a perception model which takes the image, produces some form of information about what objects are there, or some kind of a parser which takes the instruction, outputs some formal representation, or some kind of a planning model which takes all this information and generates actions. And these pipeline methods are really popular in fields like robotics and have been used for actual tasks, like manipulating forklift robots. But the problem of this approach is that it requires a lot of engineering effort in designing and maintaining. For example, if you build this pipeline, you have to design what intermediate representations would you output. What would the interface between the parser and the planning module look like? So you have to build things like ontologies or some form of other structured representation. And often these representations are very hard to scale. For example, if now you want to use this pipeline for a different robot, or if the problem changes, like a different environment, then a lot of this work has to be redone. So it makes it hard to scale these methods to new problems. And these are some work which broadly have looked at this problem. So there was some very original work on using rule-based methods, like the work by Terry Winograd in 1970. And this work is very interesting because if you read about it, this work was very promising. And people felt that this shows that AI is quite achievable and will probably solve it in next few years. But then people gradually realized that this is hard to scale these kind of systems. And so eventually people started working on more learning-based approaches. And this includes a lot of work. These are some of them. So for example, the work which I really like from Stephanie Telex, then at MIT, now Professor Brown, she designed a real system which was deployed on a forklift robot and was moving stuff around in an open field. But as I mentioned, a lot of this work has been building these pipelines or assuming that a part of the problem has been solved, like the computer vision problem has been solved. And these methods are expensive in terms of engineering, and as I mentioned, are hard to scale. So what we propose is what we call the direct mapping approach. So instead of building this elaborate pipeline, we'll build a single model which will reason about the raw data, the observations, and the instructions, and generate actions. And this single model will hope that would be able to do all the reasoning that these elaborate pipelines are doing. And it has to do it while reasoning directly with the raw data, like, for example, RGB images. So let's be more concrete with a specific task. So this task was introduced by Jonathan Bisk and others and contains fairly challenging instructions for moving blocks on a map. So the instruction here is put the Toyota block in the same row as the SRI block in the first open space to the right of the SRI block. And in order to do this task, this is what the agent has to do. Remember, it's observing raw RGB images and has to find which block it has to move and then generate a sequence of actions. So here it's moving this block around to the destination shown in the red square. So this red square is for our visualization, so it's not what the agent can see. And we can view this thing as taking a sequence of actions. So we have the instruction, and then there's an initial layout of the map, and the agent has to generate a sequence of actions which involves selecting one of the block, like for example the block with the logo of Toyota, and moving it a step in the north, south, east, or west direction. And finally, the agent has to indicate that it has completed the task with a stop action. So this is the final action that the agent takes. And this actually is kind of important because we want to design agents that don't just accidentally complete the task, but actually know that they have completed the task. And this is different from some of the, if you are familiar with these arcade game environments like Mario Brothers, where if you just happen to be in the house, the game is over. So we want to design, and this is, I think, is a very important part of the problem that people have overlooked. So these actions together, so there are about 20 blocks and 4 directions, so 80 actions of this type and a special action stop. So this gives you 81 possible actions you can take at any given time step. And this is a fairly large action space, so it complicates the problem. So let's look at challenges in trying to solve this problem. So the agent observes the image of the current environment and is given the instruction and has to understand that the phrase Toyota block refers to these pixels over here, that the phrase SRI block refers to these pixels here, that the phrase in the same row as that refers to anything which is inside this rectangular grid, and the phrase in the first open space to the right of that refers to anything which is inside this red square. In all this reasoning, it has to combine and understand that the Toyota block should be moved over there, and then finally generate a sequence of actions. And in this case, has to solve, for example, some planning problems, like it has to move the block around these obstacles.
Question.
Yeah, go ahead.
It seems like there's a natural decomposition of this problem from estimating the goal state and the sequence of actions to get to the goal state.
Mm-hmm.
Because if you know where the goal state is, the rest of the language is.
Yes. So actually, the original paper does exactly that. But if you just give it the goal state, then you're kind of assuming that there is a planner which will then take the goal state and achieve it. So in this paper, we were trying to do everything together. So using a single model, and of course, so you can make several assumptions over here. For example, you only ever move a single block in this map, so you can say that. Why don't we directly predict which block and then find how to move it? But we wanted to study how much we can really do with a single model without encoding assumptions. Because let's be honest, I mean, this task in itself is not interesting. So it's as interesting as a test suite for then developing models that we can then apply for more realistic tasks. And we will look at more realistic tasks as we move forward. So these challenges that we discussed could be put in 4 categories. So there's the first challenge, of course, of understanding these complex phrases, like in the same row, what to the right of, and all. And then you also need to do image understanding. You have to understand what kind of objects are there, what are the relations of these objects. And finally, you need to move blocks around obstacles, involves some amount of challenges in the planning. And most importantly, the way I see it, the most important challenge is learning. So here we are generalizing to new instructions and images at test time. So this is kind of different from more like the standard reinforcement learning setting where you train on a game and then you test on the same game. So there's a general, yeah, go ahead.
Sorry, when you say new images, you mean new configurations of those 20 blocks?
Yeah. Yeah.
Can I ask one question?
Yeah.
I'm a little confused. Is the optimization part of your analysis, or is it just the challenge of understanding the image and understanding the command and then separated by the path that you use to follow to get to the end result?
So what do you mean by optimization?
So the path optimization, is that a separate step or encoded within the whole environment that you're talking about?
So the agent has to take a sequence of actions. So the task involves doing all the reasoning simultaneously.
Okay.
And so I do want to point, as I mentioned, that this generalization part is quite tricky because it's generalizing across two different modalities. And finally, we have to do it using a very small size data set. And why that is important, we'll look at when we discuss learning later.
So, similar to the previous question about new images, new instructions also means you assume that you've seen all of the pieces of the instructions, but just not in that particular configuration.
So it will be new instructions mean new sequence of words, which could include unseen words as well.
One more question.
Sure.
If I remember this paper correctly, this is a fully observable setting, right?
Correct. Yeah.
So there's no noise in the dynamics.
No, it's a completely deterministic setting.
And so you could, like, if you open loop planning, right, nothing changes. Like once you observe and you know where you need to go, the sequence of actions are not giving you any new information. You see yourself move, like you see that block.
Right. Yeah.
But there's no noise in that.
There's no noise. Yeah. It's a fairly simple setting. Although there's like interesting combinatorial possibilities because oftentimes you have to look at multiple blocks to find the location. So and that could be challenging in a different way. So this problem is actually deceptively tricky in that respect. So remember, the agent has to take a sequence of actions. So at a given time step, what information can the agent assume access to make the next decision? So we'll call that information as the agent context. So at a given time step, the agent, of course, has access to the instruction, it has access to the current and the previous images it has observed. And we'll assume that the agent memorizes the action that it has taken in the past. So we'll put all of this in one category, call it the agent context, and give us this symbol of ~s. And this is all the information that the agent has to make the decision. So there's no access to any structured environment here. So once we have defined this agent context, we use it to generate actions using another concept called the policy. So policy is this box which takes the context and outputs a probability distribution over the action space. So here the second action has a probability of 0.2 and corresponds to moving block number 10, which is the block with this logo, a single step in the south direction. And we give the symbol of pi to refer to the policy, and by pi a given ~s, we mean the probability of taking the action A when given the context ~s. Now remember, our aim here is to design a model which doesn't use any expensive engineering or.
Sorry, one last question. And you're allowed to move the reference blocks.
You're allowed to move any blocks possible.
I see. So another solution to the thing you saw earlier was to move the SRI block to the left of the Toyota block.
So let's see. I would say that's not necessarily following the instruction because it specifically says that you should put the Toyota block. Although so that would actually, even our evaluation metric wouldn't like that. So you will be penalized actually for doing it. So our aim here is to minimize engineering effort and not use any external knowledge base. So to do that, you'll design a policy model to reflect it. So we use this neural network architecture.
Are you going to define the reward function later?
Yeah. For right now, there's no reward function. We are just talking about, so that will come in the learning. Yeah. Some people like to view reward function as part of the problem, but I actually because in general in NLP, there's a reward function, but there's a separate evaluation metric. So I like to view those things as different. But I think if you talk to an adult person, they think reward function is the problem. So there is a problem specific reward function. Yeah. So this is the neural network which will define our policy. So it contains three main components. There is a convolutional neural network which takes the current and the last 4 images and maps them to a vector representation. So CNNs are a special type of deep learning architecture which have been used widely in computer vision community. Then we take the natural language instruction and map it using a recurrent neural network with LSTM nonlinearity to another vector representation. And finally, we take the previous action that the agent took and map it to another vector representation, and then we concatenate these vectors together. We project this representation into a single space and use that to generate probability distribution over which block has to be moved and in which direction it has to be moved, or if the stop action has to be taken.
I wonder why the previous images are necessary. If I just know the snapshot in one time step before, do I need the images corresponding to previous?
I think it could be useful for recovery from failure. So for example, you just moved the block wrong, then you realize that it's a wrong thing. So you still have access to previous images, which could help you, could you recover. But yeah, I could definitely come up with a policy which doesn't look at that. But I think a fair bit of redundancy shouldn't be harmful.
Also, you're probably sampling from your policy.
Yeah.
So if you end up sampling and it causes jitter,
Yeah.
notice it.
Yep. And this is I would say, a fairly simple neural network architecture. And we're not using any expensive knowledge bases here or resources here. So if you look at some of the pipelines before, and I've worked on the systems, there's often a parser, then there's some kind of a semantic map or some knowledge bases or So we're going to use a very simple network here. And we're going to hope that this can do all the things that these pipelines were doing. And it's quite simple that people have been able to use it for other tasks, like this recent work at iClear. So now that we have defined the policy, how do we go about training? So to do that, we're going to make certain assumptions on our learning setting. So we're going to assume that for each example, we have access to a demonstration. So demonstration is the sequence of context and actions. And so here, S tilde1 is this initial context. A1 action is the action that the Oracle policy would take if this context was given as input. And then S tilde2 is a second context, and then so on. And the idea is, because as I mentioned, it's a deterministic domain, if you follow these sequence of actions, you perfectly complete the task. Okay? So that's the assumption number one we're going to make. The second assumption is inspired by work in robotics, where during training, we're going to assume access to the world state to be able to provide feedback to the agent. So this world state here contains information about what objects are present in the world and what's their position and configuration. And these are some papers where this assumption has been made. And generally, the way you make this assumption is that you place some monitoring or some kind of cameras which measure the position of these objects. And so you're essentially training the agent in this very controlled lab setting, and then you will deploy it in this open setting where this assumption cannot hold true. So that's the motivation behind this assumption. Now for each example, since we have already assumed access to the demonstration, a very simple thing we can do for training is supervised learning. So supervised learning takes this demonstration and maximizes the log likelihood of actions in them. So mathematically, you solve for this optimization here, where the theta is the parameter of the neural network policy we saw. The expectation is over examples in the training data. The summation is over the steps in these demonstration. And AI is the ith action, and S tilde I is the ith context. So you solve this optimization by sampling using your training demonstrations and do simple updates using backpropagation. And people have used it. It's a very old approach. For example, Pomerleau used it for autonomous navigation in the 90s. Sorry, what?
It's older than that, too.
Yeah. So we could do that. But the problem is that an agent that is trained using supervised learning finds it hard to recover from failures. So if an agent makes a mistake, what ends up happening is that there starts happening a mismatch between the train and the test time state distribution, which affects the performance. And it goes by various names. Some people call it exposure bias, for example. So mathematically, this is the mismatch which happens. So during training, you're optimizing this objective. So here states are sampled using the perfect distribution, the oracle distribution. And the actions are from the oracle, and you're maximizing the log likelihood of these actions. But during testing, the agent takes actions on its own. So now the distribution over the state is induced by the agent's policy. But you're still optimizing for the oracle action. So now this distribution is different from this distribution. So there's a mismatch. And when distributions are different, we shouldn't hope that the performance on a different distribution would be very good. And this problem is called exposure bias or goes by various names.
So
Like code.
You can actually training your model by sampling, right?
No, so for supervised learning, you can just assume that you have an oracle demonstration, and you just maximize the actions.
You can construct your shortest path to your target, and then you can whenever you sample your next step, you can construct the following step, and then you can use it to supervise your next.
Oh, so I think what you're getting at is imitation learning. You can totally do that, but you have to make an assumption that you have access to the model of the environment. And that assumption is actually very hard to realize in practice. So I can talk about it when we discuss the learning. So the goal here is now to design agents which can learn to recover from this failure. And a very popular and powerful paradigm which has been applied for various tasks recently is the reinforcement learning. So in reinforcement learning, the agent samples actions according to its current policy. For every action, it receives a reward. And the aim is to maximize the expected total reward, which is I'm showing by this figure here. Here, the expected means the expectation both with respect to the examples in the training data and also with respect to the actions the agent takes for any single example. And the total reward is a sum of reward it receives for any one example. So that's the objective here. And the idea is that by learning to explore, you kind of would be able to recover from failure. So there won't be a mismatch between test and training. But we haven't talked about the reward function yet. And this is kind of important because in the heart of reinforcement learning algorithm is the reward function. That's the way you encode the problem that you want to solve. So in our case, the problem we want to solve is to reach the goal state and do so in as few steps as possible. So a very simple reward function which encodes that behavior is this. So we give a reward of +1 to the agent if it reaches the goal and stops there. We give it a negative reward if it causes collision or stops in the wrong state. And we give it a small negative penalty for otherwise to minimize the length of the path, because there could be multiple ways in which you could complete the task. And we could write this reward function because we have already assumed access to the world state. So we know where objects are, where the agent is. So this reward function is pretty easy to program. And so now that we have used a reward function, we can use a very standard reinforcement learning algorithm. Later. We'll come to it. So a very standard reinforcement learning algorithm is the policy gradient learning. It's actually more like a family of reinforcement learning algorithms. But the way it generally works is that the agent samples actions by using the current policy and generates what's called an experience, which is here. So this experience contains the states, the context, the actions sampled using the policy when given the previous state, and the reward the agent receives. So we generate this experience, and we use this experience to optimize the objective, the reinforcement learning objective. And there is a standard way, there's a theorem by Richard Sutton, which allows you to compute the gradient of this objective called the policy gradient learning. And using this experience, you can approximate the gradient with this formula. So this formula here, we are summing over the steps in the experience. The pi, remember, is the policy. AT is the Tth action. S tilde T is the Tth agent context. And Q is this multiplicative factor which measures what's the reward you would receive in the long term if you take action AT in context S tilde T. So you can think about this multiplicative factor as some kind of credit. It's like, how good is this action if I take it now? And this credit takes into account the entire long-term effect of this action. So this completes the reinforcement learning algorithm. But the problem is that these algorithms are quite data hungry. And this has been theoretically well studied. For example, Sham Kakadi's thesis has a good deal of information on this. And it has also been empirically shown in a bunch of recent work on using deep reinforcement learning. And this, I think, is very challenging for instruction following or natural language understanding in general. Because remember, our context contains instruction. And instructions are written by human beings. So this makes it hard to scale these data sets to be able to apply these reinforcement learning algorithms. And this is critical. It kind of makes it hard to use like vanilla reinforcement learning here.
So you mentioned there are multiple possible ways you can reach the goal state from the initial state, right?
That's true.
So I guess that would be seen in the policy, the actions that you're sampling. But is there explicit some type of entropy that you try to maximize the distribution that you're sampling?
Yeah, so we do entropy regularization. Yeah, that's kind of critical. So these algorithms are very finicky. You have to optimize for several things. But anyway, I think in general, in spite of all the work, I mean, the problem still remains that reinforcement learning algorithms have high sample complexity. So what we decided, that instead of working with arbitrary reinforcement learning problem, we'll work with what's called the contextual bandit problem. So this problem is inspired by a much older work called multi-arm bandits and was introduced in this paper by John Langford and Tony Zhang in 2007. So in contextual bandit algorithm setting, you maximize only the immediate reward. So you can think about a setting like a user comes on a website. Your task is to show an advertisement to the user. And then based on whether the user decides to click on the advertisement or not, you get some reward and the task ends there. So it's just a single step reinforcement learning problem. And theoretically, it has been shown that this problem has lower sample complexity than reinforcement learning. What that means that if you have fewer samples, you can create a better contextual bandit agent than a reinforcement learning agent. But as I mentioned, that these methods are designed for a single step decision making. So it's not, and in our case, the agent has to make a sequence of actions. So what we did was adopt the contextual bandit setting for reinforcement learning. So we're going to apply an approximation, which will give us this algorithm here. So this is a new algorithm. We call it contextual bandit policy gradient. So the step one remains the same. You still sample actions according to the policy. But in the second step, when we compute the gradient, we'll apply an approximation. So this is an approximation here. And we'll only optimize for the immediate reward. as opposed to the Q function that we had before, the Q term, we only have the immediate reward here. And this will give you a biased gradient, actually, but would reduce your performance. Like so in the sense of, it will give you lower error with fewer samples. So there's an approximation here, and this is the contextual bandit approximation, that at each time step, you only care about maximizing the immediate reward. But there's still a problem. The reward function that we saw a few slides before is extremely sparse. So this is for the example we considered before. Here the blue line, or the purple, shows the demonstration. And the color on the map shows how much reward would you get if you place the correct block over there. So as we can see, the agent never gets a positive reward until it actually reaches the goal and solves the problem. And a policy in the beginning is going to be randomly initialized. So it's going to be as good as a random walk. And the probability that a random walk would reach here is negligible. And this makes it very hard to do reinforcement learning using these reward functions. Some people call them sparse reward function informally. But this is even more problematic in our case because we are training the agent to maximize the immediate reward only. And the immediate reward here is pretty meaningless. It just gives you -1 or a negative penalty. So what we did was to use a technique called reward shaping to change the reward function and add an informative shaping term shown here in this symbol F. And we use a new reward function, which we hope is richer, so not sparse, that we'll then optimize over. A few slides before, I just said that reward function is this heart of reinforcement learning, and it defines the problem we are solving. So if I use a different reward function, how come I am solving the same problem as before? So there's these theorems called the shaping theorem, which says what form of f can be such that the new problem is the same as the old problem. So one theorem here from Andrew Ng 1999 paper is that if f has this functional form for some function phi, then we'll maintain the preference over the policy. By what I mean is that if we prefer policy pi1 to policy pi2 with respect to the old reward function, we'll prefer pi1 with respect to pi2 with respect to the new reward function. So the ordering over the policy is going to be the same. So we use this shaped reward function to modify our reward function from being sparse to being more rich. So in a nutshell, we add a shaping term which incentivizes the agent to move close to the goal state and also to follow demonstration. So we add this extra information in our reward function. So I don't have time to discuss more of the detail, but if there's a question, I'll be happy to dive in. And so that's going to be our main learning algorithm. We're going to do a contextual bandit approximated reinforcement learning with a shaped reward function.
Can you give a sense of just like how expensive it is to get that?
To get this reward shaping? OK, great question. So the demonstration, I would assume, is not super hard to get. But what is hard to get is the first term here, which is also the more important of the two shaping terms. And the way you do it is that we assume access to a distance function that if you give it 2 states, it's going to compute how far they are. In general, getting this distance function is tricky. But for this problem, we have been able to learn it. And we learn it using what's called a metric learning. So we have access to a bunch of contrastive data. So you have 2 states which are close and 2 states which should be far. And we do metric learning to learn a distance function. But in general, this could be hard. So for evaluating our agent, we'll.
One quick question. So if you're making all of these assumptions about the environment that you can actually get access to not just imitations but also the reward shaping term, and at that point, it's just as expensive to do something like Dagger.
Dagger needs one more assumption. So you could do something, as you suggested, a shortest path, like where you take an action and then you want to tell that which action at this state is going to give me the right behavior. But then you need to know what's going to happen if you take that action. In our algorithm, you take an action and only then you compute the reward. But for the Dagger, you need to mentally assume that what's state going to look like if you take this action. So you can do Dagger, but it's one more assumption that you need the model.
This environment has no noise in its dynamics.
Right, but Yeah, so I mean, as I said, I mean, this we're not really. You have to make that assumption in general.
But in general, what your reward or your shaped reward looks like is a distance transform, right? So if I were just to compute the shortest path distance from every point to the goal state, that would be an excellent choice for my reward and for what Drew was talking about, right? So
the way I was saying is that if you are at a given state and you want to do, so Dagger is a very strong algorithm. It gives you very, very strong feedback. If you're in a given state, you want to find what's the optimal action to take. Okay, unless you're assuming backtracking, that you take the action, you go back, then you take, so you have to understand what's the best action to take at this given point. And that's kind of requires you to understand that this is the state I would be in if I take this action for all possible actions. So you need what's equivalent of a model. So you need like a one-step model. So you have to do model-based learning. If you're ready to make that assumption, and I think in the block world you could learn that, then you can perfectly do that. I think that would be a very strong algorithm. But there is that assumption. It's kind of hard to see because it's a block world. So, but eventually we'll go to more realistic problems. So the setup here, it was introduced by the original paper from Jonathan Bisk. It contains a small data set of about 12,000 trained instructions and 3,000 tests. But during testing, we are working with unseen instructions and maps. And the execution error that we'll be evaluating the agent on is the distance between where the blocks end up being and their goal position. So we compute these pairwise distances and sum them, and that's the evaluation metric. And these are the results. So we compare our algorithm against these baselines. The stop baseline just takes the stop action at the beginning of the task, so it doesn't take any actual action. The random walk here takes samples and action randomly uniformly and performs even worse, as we can expect that a random action would make situation bad. Supervised learning algorithm performs better than these. Deep Q learning and reinforce are two popular reinforcement learning algorithms, or at least were popular 2 years ago, and they perform kind of like bad. And finally, our contextual Bandit algorithm outperforms these baselines.
What's the error bars on that measurement?
You mean the variance? So I don't have.
How much data did you use to get those? Are those really tight or are they relatively broad?
So for these ones, I mean, so I don't remember the results for each one of them. So these are, of course, yeah. I would assume about 0.2. So 3.9. I've seen it go up to 3.9. And these are this is an example, and these are agents trained with the different learning algorithms. The instruction here is, move Mercedes to the left of Heineken, slide up far enough to clear Heineken, slide right until almost touching shell, slide up evenly until evenly aligned with shell. So let's see what the agent with supervised learning does. So it takes a first wrong action and then just completely fails to do the task. The agent which is trained with DQN has a hard time. It doesn't take any action properly. And I have some ideas about why this is happening, and I'm happy to discuss offline. And finally, the agent trained with our approach is able to do the task. And this is a failure case.
One question is this comment, this instruction example reminds me that my earlier point about disentangling cohorts incorrect. This instruction is describing the form.
So we did some qualitative analysis of how often that happens. And we saw that in about 92 to 90% cases, it mostly talks about where you should eventually end up being. So your comment is roughly still correct. So this is a failure case. Here the instruction is slide block 18 to the right and that up so that it is directly under block 17. So an agent that is trained with our algorithm performs this up and down oscillatory behavior, and we call it the stopping problem. And one reason why I believe this is the case is because it's a label bias problem here. Because if the agent tries to stop anywhere else, it gives it negative feedback other than the goal state. So the agent really learns that stopping action is the last thing it should do. And that's why you see this kind of behavior. And this is bad because in real life, if you don't know how to stop, then bad things happen to you. Okay. Okay, so I'm gonna skip this in the interest of time. So let's look at a different task. Okay, so here we are going to move to something which is more realistic, which is 3D environments. So all of us here live in a 3D world, and when we go to a different city and we ask for directions from someone, we often have to do this spatial reasoning. So to test if we can design agents to do this kind of reasoning, we collected a corpus which has instructions for an agent navigating in an open land space. So here, the instruction is, walk towards and around the back of the ladder and take a left. Walk past the pumpkin and towards the gray boulder and stop before you reach it. So the agent observes the world in this first-person view, and this is a top-down view of the agent. And in some way, this is a more challenging data set than the block world, because in the block world, we were in this very top-down pixelated environment where the blocks are generally placed left or right of each other, or you build a line, so you build these diagonal things. But here, the instructions are much more ambiguous. For example, there is no precise stopping location. And this makes spatial reasoning and evaluation both hard. The other challenge is that here we are working in a 3D environment. And so the problems like occlusion and scale start to become real. For example, here we see that the statue is partially occluded by the ladder, and objects which are away from the agent are smaller than the objects which are closer to the agent. And this is different from the block world where all objects are of the same scale, and there is no occlusion here. But the task still remains the same. So we're still solving instruction following. Agent has to take a sequence of actions and indicate completion with the stop. Here, the action space is different. So the agent can move a step forward or turn left or right by 30 degrees. So remember, when we talked about the previous problem, we created this concept of an agent context, which is the information the agent has in order to take actions. Here, we're going to use a slightly different an assumption for the agent context. So like before, we still have access to the instruction and the current and previous images. But we're going to assume two more things here. We're going to assume access to the agent's pose, which is the position and the rotation of the agent. So we have this extra information, and this is fairly common in robotics, and there are algorithms which give you that information. Another assumption we're going to make is access to a panorama of the agent's surrounding. And the reason why we do so will become clear pretty shortly. So remember, we said we are interested in designing agents that can learn to do spatial reasoning. So what was wrong with the original model we looked at in the first half of the talk? The problem was that because of the black box nature of the neural network we saw before, we don't know that the agent has understood the task without taking actions from the agent, from the policy. And this is in general a very unsafe and horrifying thing in the worst case to do, because you don't want an agent to take actions when you don't know it has understood the task. So how do we design agents that even prior to starting to do the task, starting to take actions, give you some evidence that they've understood the task? And this will have an advantage like interpretability and safety, so we can understand where the mistake is being made and if the agent even understood the task to begin with. And we'll do this interpretability using this decomposition. So we'll break down the instruction following task into two subtasks. We'll first predict where the agent should go given the instruction and the image. So given the panorama and the instruction, we'll do a goal prediction to generate a distribution, and then use this prediction to generate actions using the pose and the action generation model. So we're going to decompose the task this way. And this will have two advantages. One, as I mentioned, is about the interpretability. And the second advantage is that because we are going to remove the language understanding from the generation part, it's going to make the learning problem for the generation easier. So let's look at the first problem here. So given the panorama and the instruction, the goal prediction part will generate a distribution where the pixels here show how confident the agent is that that's where the goal is located. And we're going to frame it as an image-to-image problem that is conditioned on the natural language. So when we thought of this decomposition, we looked at the computer vision literature for models which do this kind of image-to-image conversion. And one model that we found is quite powerful is the UNIT model from Ronenberger 2015. So it was designed for, yeah?
This panorama-based prediction makes sense because
Yeah. So, yeah, in the same paper, we have another data set which does have walls. There, what we do is that we do a panorama, predict the next goal, then we do another panorama. So we do it a multiple way. So for example, if you decide that you should go in another room, you first go predict the door, go through it, and then go to the. No, but we have a heuristic which predicts like what the intermediate points look like, or what the decision states look like. So here, the UNet model takes the input image and performs a sequence of convolution operations followed by a sequence of deconvolution operations to generate an output image. And the idea behind it is that this allows you to do hierarchical reasoning. So you have these stack of convolutions which can do reasoning at different scale. And then you have the opposite operation which allows you to regenerate the image back from these convolutions output. But there's no natural language here. And in our task, as I said, there's a natural language conditioned reasoning. So we took this model and modified it to do language-based reasoning. And we get a new model called the LingUNET. So the way we do it is use an LSTM to map the natural language to a vector representation, and then use this vector representation to do text-based convolution at every layer of the model. And the idea is that because these convolutions are doing reasoning at multiple scales of the image, now we can do text-based reasoning at the different levels, at the different scales of the image. And we use this LingUNET model to generate the goal distribution. And the action generation model, which takes the distribution and the agent's pose and then generates the action. And this is a very simple architecture, has a simple LSTM-based recurrence and does some camera projection to map these pixels to ground location. So in the interest of time, I'll skip over the details because I don't think they're very super interesting, and then talk about the learning. So here now we have two different models. We have a goal prediction model, and we have an action generation model. So what we do is we find that the different type of learning is better for the different models here. So for the goal prediction, we use a simple supervised learning to minimize the cross-entropy loss. So here we don't have any kind of a mismatch problem. So our simple supervised learning here works perfectly well. For the second model here, the action generation, we use the algorithm we introduced in the first half, the contextual Bandit algorithm, and use that to train the action generation model. But the key thing here to note is that there is no natural language here. So the agent context doesn't occur, it doesn't have natural language. So we could potentially scale the data set by creating synthetic input-output examples for training the action generation. So this simplifies the learning, and we get pretty high accuracy for action generation. Go ahead. Mm-hmm. Yes. So, great question. So in this case, no, because we are training them specifically to go towards the goal. But in another paper at Coral, what we do is instead of predicting only the goal location, we predict the path as well. So we do. So, but that's a different paper. I won't be talking about it here. But yeah.
Question?
Yeah. Sorry. Go ahead.
So if you go back, yeah. So when you do the image, this is the first person view. How do you incorporate? So when you predict the distribution in that first person view, how you figure out the depths of the point? Because if I see this direction, the points are along this direction, any depth will be the same points showing.
So okay, maybe. So if I understood the question correctly, like how do we go from here to actually being able to reach the goal? Like even if you predict it perfectly. So the way we do it, I mean, I'll tell you very briefly, and we can talk more after the talk. Essentially, we do camera projection to predict the pixels to a 3D location in the real world, and then we constantly track that 3D location at every frame. So that's why we use the agent's pose, because for this task, given the height of the agent and its position, you can easily write down the camera projection equations. Yeah, so let's maybe I'll skip some part and we can go towards more interesting. So we collected a new corpus, which is slightly bigger than the block world corpus. It has about 20,000 train instructions and 4,000 dev and test. And the evaluation metric would be the distance between the agent's final position and the goal position. So we still use this stop distance-based evaluation metric. And we found that it correlates reasonably well with the human evaluation. And these are the results. So the stop and the random walk baseline we saw before continue to perform bad. Misra 17 is the architecture and the learning algorithm we introduced before. So it performs better, but still quite bad. The Chaplot 18 is an architecture and a learning algorithm from CMU. It actually performs the full reinforcement learning, uses what's called a generalized advantage estimation. And finally, our model outperforms these baselines and has a key advantage of interpretability. So we can actually look at these distributions to see where the agent makes mistake. So let's do so. So over here we see these panoramas with the goal prediction superimposed on them. So the first instruction is fly between the palm tree and the pond. And we can see the agent is quite confident that the goal is between the palm tree and the pond on the right. The second instruction is curve around big rock, keeping it to your left. And we can see the agent has some confusion over which side of the rock it should go, but the mode of the distribution is still on the right side. And this is kind of interesting because the distributions give you more than mode. So they give you the what's the place which are confusing the agent and the variance of the distribution. And these are some failure cases. So the example at the top here, the agent goes on the wrong side of the mushroom, maybe because it's confused by this lake-like body here. And over here, the instruction is just too vague. So as you can see, the distribution is all over the place, which is kind of what we expect. So we also did some quantitative analysis of the paper. If you're interested, you can look at me. So let's skip this and talk about some recent work that I've been working on. So in the same paper that we introduced this problem, we introduced an even more challenging setup of doing navigation and manipulation in a 3D house. So we built this simulator using Unity 3D, and we have this agent which can do manipulations like pick objects, move around, open drawers, and even can turn on televisions and stuff. And this is a much harder problem because, as Dhruv mentioned, it has these kind of walls, and you have to navigate between rooms. And you have instructions like clean the table, where you have to keep on move and pick stuff and keep them in the sink. So much harder language understanding and much harder planning. And this is an open challenge. So if you're interested, we can talk about it, and I can tell you how to use the repository. So let's skip this as well. Let's talk about some recent work in the next couple of minutes. So we looked at some of these simulated environments today. And in general, simulated environments have been gaining momentum and popularity in the learning community because they allow you reproducibility. And it's very easy for people to use. You just have to do git clone and you get started. And they're greatly useful. I think we're learning new stuff using these simulated algorithms, environments. But in general, real life is much harder. And specifically, real life has much harder control problems and much harder image understanding. So there is a gap between even the best simulated environments we have today and the real life. So to understand how big is that gap, we looked at these two problems in isolation. So in this paper recently at Coral with Walls, Ross Nepper, and Yoav Adzi, we looked at the task of mapping observations and instructions directly to velocities of the control of the drone. And this drone we used provided by the Microsoft AirSim, so it has dynamics and a fair bit of complexity. And we were able to get some reasonable performance, but I think we can still keep on pushing it even more. And in the second paper recently at CVPR with Howard, Elaine, Noah Snavely, and Yoav Adzi, we looked at doing navigation in a map of the Google Street View in New York. Here the agent has to observe these challenging real-life images and has to follow actually even more complex natural language instructions. And this is an open problem. We have some navigation results which are quite poor, and I think there's a lot of room to go on these tasks. And finally, we talked about a lot of these simulated environments today and the models. So we have built this integrated learning framework which has implementations of these models, these learning algorithms, and stuff. So if you're interested, you can check out the repository here. And finally, this is also my last slide. So I talked about instruction following today, where you give an instruction to an agent, and the agent is expected to follow. But in general, there's like the real life has much more complexity. For example, people learn by interacting with each other, right? So there is a dialogue. The real life is like you can ask clarifications, for example, if the task is not well formed, or you can ask like, okay, did you really mean this thing? If it's something completely garbage. So there's directions like working more on dialogue side. So like doing task-based dialogue understanding, and some of the work has been coming from like Dhruv's lab as well on these kind of problems. The second problem is that how do we evaluate these problems? So I talked about some metrics like stop distance, but in general, these metrics could be very poor proxy because you can have instructions to talk about intermediate goals, or something more subtle. So how do we go about like designing better evaluation metrics for these problems? And I think this is in general present in other natural language understanding problems as well, like machine translation, where people have shown that proxy metrics like BLUE are not very good. And then how do we design better learning algorithms which can do, for example, some complex exploration and work with limited amount of data? And lastly, like here we use a reward function that we computed using the environment. But in general, people give each other feedback all the time using natural language, right? I mean, you did a great job. You shouldn't have done this. You should have done that. So how do we take this natural language feedback and map it to a scale of reward and use it for training agents? And this could be a great assistant for like things like Siri and in Cortana. So I'll stop here. Do you have time for questions or probably?
Questions in the middle. If there's one quick question, we can take it now, but otherwise.
Yeah.
One question. So in your talk, you held two contradictory views about how much structure should be in these models. An end-to-end simple model is great because it's simple, and then later, no, we need structure so we can understand what's going on, etc. So what do you really think?
Okay, great. That's a great point. That's a great question. So let me tell you how we went about it. So in the first paper, we're trying to really push how much we can do without doing any expensive engineering. Like think about that as a baseline. Like this is going to establish the baseline because you're not going to make any assumption. I would assume the answer lies somewhere in the middle, but closer to end-to-end metric. So in the second paper, we went slightly towards the left because we realized that these single black box-based models are kind of just really dangerous to even deploy. And what we ended up happening was we were using these models, but if they make an error, we just can't do anything about it. We don't have enough understanding about why these models are making error. So there's debuggability issue, and then there's, of course, a safety and interpretability issue. So we went a bit towards the left, I would say, towards more engineering. But if you think about it, the kind of engineering we have assumed here is scalable. So you can use it for different environments. Like things like goal prediction, you can always do if you have image and text. So we're not really introducing ontologies. So if you're familiar with like these semantic parsing-based methods, you introduce ontologies which are very hard to scale to new problems. So we are introducing some level of engineering, but not as much, which makes it very hard to scale to new problems.
Cool. We'll stop here. Let's thank the speaker again.